All right, so this is the first of our series of pre-lecture videos. We're using these videos to help you understand the material that we're going to cover in class and that you read about before we go to class. And hopefully getting a brief introduction to the main concepts that we'll be covering in class will allow us to go into more depth during class and do more examples and more group work during the class. So our first study of motion our first study in our class is called kinematics, which is the study of motion. When we're studying motion, we can study things like a motorcycle, balls rolling on a pool table, or birds flying through the air trying to kill the pigs. So we're going to be concentrating on straight line motion at first. That means we won't be talking about the angry birds quite yet. That'll be in 2 more chapters that go in a curved line. But we'll be concentrating on things that go, back and forth along a horizontal line or straight up and down. So that's what we mean by straight line motion. When we're studying the motion, some of the terms or definitions that we have to be familiar with are things like displacement, average velocity, instantaneous velocity, which is also known as just velocity because it's easier to say, speed, average acceleration, and instantaneous acceleration. In addition to understanding the definitions, we also want to understand how those definitions are related to graphs of the object's motion and how we might be able to find those quantities on a graph. So the first thing that we're going to need to know is how do we describe the position of an object? It says here that the position is defined in terms of a frame of reference. Now, when you hear frame of reference, that sounds a little complicated. But all that we mean when we're talking about frame of reference is, what are we measuring the position relative to? That is, where is the position equal to 0? Where's that location? And then in what direction are values positive and in what direction are position values negative? For example, we might want to be studying the motion of these runners in the race. Now, during the race, of course, at first, they start at the starting line. And so this might be our position x equals 0. When we're defining our frame of reference, we're going to say the starting line has a position of 0. As they progress down the track, they will have positive position values that, of course, are going to increase. If someone made a big mistake and went backwards, that person would have a negative position value. So all that we mean by the frame of reference is where is the value for the position, where's the location where the position is 0, and in what direction will the position values increase, and in what direction will they decrease. So as these runners are going down the track, you see that a little while later, they're all at slightly different locations, and so they would have different positions. If we want to describe the motion of these runners or any other moving object, what would be great to have would be different position values at different times. And so as an example, I got values for Usain Bolt's 2009 world record 100-meter run, and here we see that we have his at different times what was his position. And so that is the kind of information that we would want to begin with when we would be studying the motion of an object. Once we know the positions, one of the things that a definition that we'll be working with is the displacement, which is really just the change in position. So the displacement is just one value of a position minus another value of the position. So depending on what 2 positions we would use for Usain Bolt's we could have a displacement of 100 meters over the course of the entire race, or we might look for his displacement during a shorter time interval. The information about his run I first gave you in the form of a table, which sometimes is difficult to really get any sense of what's going on because it's just a series of numbers. But when we put it on a graph, and in this graph, the vertical axis represents the, actually this one represents the time, and this one represents the position. Actually, just to be clear, we usually would make a graph of position versus time for our own uses. But in any case, a visual representation of the numbers is always helpful to have. So, moving on, another definition that we want to be familiar with is average velocity, which basically gives you a sense of how fast the object is going. You choose 2 points in the motion at 2 different time locations, and you look at the displacement between those 2 times, and then you divide by the change in time. Now, since this is measured in meters and time is measured in seconds, average velocity will be measured in meters per second. On a graph, the way that we look at average velocity, it's kind of nice to see how we would find it on this graph. So this is a graph of a different kind of motion. We'll look at it in class on the first day. But we might choose 2 points on the graph, and then we want to find the average velocity. So we're looking at the change in the position, the displacement, and remember, this graph is preferable to the one we saw from Usain Bolt because here we have the position on the vertical axis and the time on the horizontal axis. And so if we're looking at the average velocity, notice that we have, by definition, it's the displacement over the time, but notice according to the graph, it's the rise over the run, which is equal to the slope. So it turns out that when we're finding the average velocity on a graph of an object's motion, it's actually the slope of the line that joins the 2 points. Now, if we did different average velocities for different time intervals, notice on this graph is showing 3 different lines which would represent average velocity for 3 different time intervals. Notice how they have different slopes. And so this means that in this object's motion, the speed of it is changing depending on what the time interval is. And so in those cases, average velocity isn't as useful as we would like it because it doesn't seem to really very specifically describe the motion of the object. We would like to get a little bit more precise. So what we're talking about then is the instantaneous velocity, which is how fast is the object moving at a particular time. So for average velocity, we were looking at displacement over a time interval. When we talk about instantaneous velocity, we actually want that time interval to be shrinking down to 0. So here you see that we're still looking at the ratio of displacement over time, But mathematically what we want is we want to let that time go to 0. And now this might look familiar to you because mathematically this is the definition of a derivative. So the velocity, which remember that's shorthand for instantaneous velocity, is the derivative of the position with respect to time. So we go back to our graph, and again, remember we had these 3 different average velocities, and the average velocity was found by finding the slope of the line joining the 2 points. Well, what we do to find instantaneous velocity is the slope of the tangent line. So remember back to geometry, a tangent line touches a curve at just one point. So if we drew a line that was tangent to the curve, here it's tangent right here, and we found the slope of that tangent line, that would give us the instantaneous velocity. 2 more definitions until we're done. In the previous picture, we might have noticed that, and I'll just redraw it here, this was position versus time, and the curve looks something like this. Notice that the tangent lines, if we draw them at different locations, they'll have changing slopes. This means that the velocity is changing. And in those cases, what we want to define is the average acceleration, which is the change in velocity over the change in time. Again, we have the average acceleration, which is the change over some time interval. So for instance, we can look at, here we have 2 different graphs. Well, it's one graph with 2 different data sets on it. The blue line is Forrest Gump running, and the green line is Usain Bolt. So if we wanted to find the acceleration, we might look at the velocity at 2.1 seconds, and maybe we would find the velocity here. And so we're using these 2 slopes, which would give us 2 different velocity values. We could then divide by the time interval between the 2, and then find the average velocity. The average acceleration, sorry about that. Just like we had previously with velocity, sometimes the average acceleration isn't really what we're after, but we want to know the acceleration at a particular instant in time instead of over a time interval. So we take, again, the definition of average acceleration, but we allow that time interval to become infinitesimally small. We allow it to approach 0, which by definition is the derivative of velocity with respect to time, or because of the fact that velocity is the derivative of position with respect to time, when we take the derivative of velocity, we are really taking the second derivative of position. Acceleration is going to be measured in meters per second over second, which is in meters per second squared. And so we can actually use a velocity versus time graph to find both average acceleration and instantaneous acceleration. The average acceleration is similar to average velocity, where you choose 2 points on the line, on the graph, draw a line joining the 2, and the slope of that line is your average acceleration. But for your instantaneous acceleration, you would want to draw a line tangent to the curve, and the slope of that tangent would be the instantaneous acceleration. So those are the basic concepts that we're going to look at in class on Monday. Hopefully this video helps you out, and it's something you can go back to if you need to review.